All right, so we're going to pick up where we left off last time talking about ionic compounds. We sort of learned first how to figure out what the charges were, and then we learned how to name these things, and then finally how to put them together to get the formula here. So now we're going to work on going from the name to the formula. All right, so given a compound name like barium chloride, how can I figure out what my formula for that compound is? All right, and there's one thing we got to keep in mind when we're trying to construct these formulas for our ionic compounds, and that is that it's all about the charges of those individual ions, right? That's how we figured out how to put these things together to cancel everything out and give us this neutral compound. We were always focusing on the charges of those ions, and that's how we got our formula, right? So, given a compound like barium chloride, how am I going to turn that name into the formula? The first thing I need is the charge on the barium ion and the charge on the chloride ion. So I'm going to have to hunt these down on the periodic table and figure out what their charges are. Okay? So barium on our periodic table. So first of all, we can note there's no Roman numerals, right? So I know that's going to be a type 1, so most likely located in one of these two columns here. And indeed, here's barium. Chloride is then going to be on the opposite side of the table where the nonmetals live. All right, so based on those positions there, take a second and tell me what my charge of my barium ion is and the charge of my chloride ion. Okay, remember with positively charged ions, what do we call those? The cations, awesome. So we do +1. Barium lives in this column here, so that's a +2 charge. What about the chloride ion? -1, right? These noble gases, they don't form ions. But then we just start counting over. So absolutely, okay? So don't skip this step right here when you're starting out. You want to draw your ions because you need to look at those charges to know how to put these things together in order to cancel out and create this neutral species here. Okay, so remember we had this trick, this swappy swap method here, where we're going to take this number on my cation, bring it down here. Take this number on my anion, bring it down here. So Ba1Cl2, but then convention is that if it's a 1, you don't bother writing it. All right, so my barium chloride formula would be BaCl2. All right, so step 1, we're going to draw these ions with their charges because it's all about the charges. That's how I know how to put these things together to get my formula. All right, so let's try it again with iron 3 oxide here. Everybody take a second and see if you can't give me the chemical formula for iron 3 oxide. So iron has this formula Fe, or rather symbol Fe. What's the charge on that iron ion? That's what the Roman numerals are telling me, right? Importantly, let me show you the biggest mistake that people always make is they say iron 3 oxide. That is not what that 3 means. That 3 is not telling you how many irons there are. It's telling you the charge on each of those iron ions, all right? So don't make this mistake. That is not what that name is telling you. It's telling me the charge on the iron ion. And then I'm going to go and look up my oxide ion here based on where oxygen lives on the periodic table. I know it has a charge of -2. So then I'm going to play that swap game where I bring down this number my 2, put it here. So Fe2O, bring down this number, so Fe2O3. That would be iron 3 oxide. And again, there are not 3 irons in this formula. That's not what that 3 means. It's the charge on those iron ions. What's up?
I didn't know that transition metals are always plus something charge.
Because they're metals, and metals are always plus something, right? Every time you have a metal, including all of those transition metals, they're always going to form cations. You don't know just by looking at the periodic table what it is, what that charge is, what the value is, which is why we have to build it into the name. It's not just iron oxide, it's iron 3 oxide, because we have to specify what that charge is. Okay, so let's just sort of write out here step by step. Ionic compounds, again, we said that they always consist of metals and nonmetals. All right, for this name to formula game, you're going to make sure to draw your ion symbol with the charge, and the charge is the most important part because that's what this whole game is about, right? So for example, we did our barium ion and our chloride ion. And then we're going to play that swappy swap game. To get our formula. So BaCl, this number comes down here, this number comes down here. So that's how I got my barium chloride. All right. One other thing that we are going, so there's one other sort of trick to this here. If we look at another example, Mg, or let's just actually do it from scratch here. All right, we're going to do magnesium oxide. Okay, so step 1 is grab those ions with their charges. I'm going to get magnesium and oxide. So that's Mg plus 2 and O minus 2. Okay? So if we do our swap method and we just sort of bring these numbers down, we would get Mg2O2. Okay? However, for ionic compounds, we can't have any common factors in these subscripts here. Kind of like a fraction. You're not allowed to keep it as 2/4, right? You got to fully reduce that fraction. So this you would really write as 1/2. We're going to fully reduce the formula for our ionic compounds as well. We got to pull out any common factors from these subscripts here. So instead of MgO2, I'm going to divide both, whoop, that was a little big, divide both of these numbers by that common factor of 2, and this gives me my final formula here, MgO. So we got one more step here, and this is kind of a special case. It's not going to be something you have to worry about all the time, but if those charges have any common factors, you got to fully reduce that formula. All right, so on our list of things to do here, let's just say, after we do our swappy swap, we're going to fully reduce our subscripts by dividing by any common factors. Okay, so let's just do an example here. Let's do titanium 4 sulfide. Zoom in as much as possible here. We need to know the symbol for titanium is Ti, and here's my sulfide on the periodic table. So titanium, the charge is built into the name, so this is the titanium 4 ion. Based on where sulfur lives on the periodic table, it's got a -2 charge. If I do this swappy swap game here, I get Ti2S4, and then I'm done. We're going to reduce it, right? We're going to pull out any common factor. 2 and 4, what's the common factor there? 2. I can divide both of those numbers by 2, right? So my fully reduced formula here would be TiS2. Right, so again, draw the ions, swappy swap, reduce. All right, cool. So now we're going to throw a wrench in the works here, and we're going to talk about what we call polyatomic ions. Okay, so first of all, let's just pick this word apart real quick. Polyatomic. What do we think that prefix poly means? Multiple, many, right? So this is going to be an ion that consists of more than one atom. Okay, so a many atom ion. So let me give you an example here. NO3 with a -1 charge here. All right. Our polyatomic ions, that N and those 3 oxygens, it's a package deal. You will never change the formula for NO3 here. It's always going to be NO3, and it always has that -1 charge. Okay? So we're never going to break up these polyatomic ions. All right? So these are their own particles. Do not break up. All right, we talked about how we reduced our formulas for our ionic compounds. You're never going to touch the little 3 here. It's always going to be NO3. Okay? And they themselves are ions. So just like when we put our compound together, barium chloride, we took those charges and we did this swap, and we got BaCl2. We can also take this nitrate ion and make an ionic compound, and we're going to play the same game with those charges. Okay? Again, I'm not going to touch the NO3. I will have NO3 in my final formula, but how many nitrate ions am I going to need to balance out that one barium ion? I could again play that game with my 2 formulas here. I'm going to bring this number down. It's just a 1. But then I also have to bring this 2 down, right? So I need 2 of these nitrate ions. So how am I going to indicate that? Again, these NO3s, it's a package deal. So if I have 2 of them, that means I need 2 of everything. So what we're going to do is put it in parentheses and put the 2 outside. Okay? All right, so again, we said that this was nitrate. There's going to be 4 of these that we need to know. All right, 4 of these that you're going to have to memorize for our exam here. So let's make our sort of master cheat sheet. And then we'll play with putting them together and all that jazz, all right? So first, again, NO3 with a -1 charge. This is what we call nitrate. CO3 with a -2 charge. This is carbonate. SO4 with a -2 charge. This is sulfate. All right, and then the last one is PO4 with a -3 charge. This is phosphate. Okay, so I hated memorization. There are some things that it's just a fact of life we gotta know. These 4 polyatomic ions you'll see over and over and over again throughout your chemistry career. Truthfully, the list of all polyatomic ions in the world is enormous, but these ones you will see at a ridiculous frequency. So we just gotta know these here, all right? So before we kind of move on, let's just pick apart what's very similar about these. They all have that same 8 ending on them, all right? So I can tell it's a polyatomic ion if it's ending in 8, all right? The beginning of each of these names tells me what the element is at the beginning of my formula. Nitrate is nitrogen, carbonate is carbon, sulfate is sulfur, phosphate is phosphorus, all right? And then they all have some amount of oxygens on them, okay? The tricky part is going to be memorizing that nitrate always has 3 oxygens and a -1 charge, right? That's really what's different about these polyatomic ions that we can't just get from the name alone. From a name like carbonate, I know it's going to be carbon. They all have oxygens. The real trick is how many oxygens and what's the charge, okay? That's kind of what you want to focus on when you're worrying about committing these to memory, all right? And again, when we put these formulas together, it's all about the charges. Yeah, exactly. All about the charges, right? So we really need to make sure to pay attention to those charges. Otherwise, we're not going to know how to put these things together. All right? And so yes, nitrate, carbonate each have 3 oxygens. Sulfate and phosphate have 4. But then the charges, nitrate's 1, carbonate and sulfate are 2, phosphate's 3. All right, so that's what we got to sort of have in our bank here. And obviously, when you're starting out with your homework, you're going to have this cheat sheet right in front of you, right? You need to get to the point where you're not having this cheat sheet in front of you. One of your homework assignments is literally just practicing naming and drawing the formula for these compounds, and it's there for you to take over and over and over again as practice to make sure that you just have that information in your short-term memory bank. If every time you do that assignment you're looking at your cheat sheet, you're doing it wrong, all right? Do it once, get your points, fine. Then do it over until you get that stuff committed to memory, all right? The other thing is, let's just put next to these because it's very similar here. We also had an ion that wasn't nitrate, it wasn't nitrogen packaged with a bunch of oxygens, but just nitrogen all by itself, okay? And if we look on our periodic table here, that nitrogen all by itself had a charge of -3. When that nitrogen was all by itself, it wasn't nitrate. What was the name of that ion? Nitride, right? We put that IDE ending on. So let's put these right next to each other so we don't get them mixed up here. One of them is nitride, the other one is nitrate. There's actually no such thing as a carbonide ion, all right, but we do have S with a -2 charge and P with a -3 charge. I know those charges based on where sulfur and phosphorus live on the periodic table. And again, these monatomic ions, these single atom ions, we put the IDE ending on. So this isn't sulfate, but sulfide. This isn't phosphate, but phosphide. Okay? Cool. So these four, we got to know. We got to know the name and we got to know the formula. And then we're just going to treat them just like we did our other ions. There's nothing special about them. As long as we don't change this formula, again, carbonate is always CO3. I'm not going to ever make it CO2. That's going to change the ion. All right, but other than that, the name of the game is the same here. So if, for example, we wanted to create the compound sodium carbonate, we would play the same game that we did before, where we're going to look at our periodic table. We're going to write down each ion with its charge. And then because it's carbonate, I got to know that that's CO3 with the -2 charge. All right, so we have our ions. We're going to do our swap. So Na, got to bring down the 2. CO3, in this case it's just a 1. And then we would reduce. In this case, there's nothing to reduce here. Okay, now let's just note that here we're going to say that since we only had one carbonate, we're not going to use parentheses. Okay, unlike our previous example where we had 2 nitrates, so we had to use the parentheses to indicate that we had 2 of those whole package deals. But if we only have one of them, we're not going to put it in parentheses. Okay, so here would be my formula for sodium carbonate. All right, let's just do a few more of these. Let's do magnesium, phosphate, and then let's also do magnesium phosphide. So we can stack these next to each other, these 2 examples. All right, so I'll tell you based on where magnesium lives on the periodic table, it's Mg+2. And I want you guys to finish off these examples for me here. right, so let's do the phosphide first because that's kind of the easier of the two that we went over last class. Again, I'm going to write down my ion formula, P with a -3 charge. I'm going to play that swap game where this 3 is going to come down here, this 2 is going to come down here, so I get Mg3P2. All right, am I done or do I need to reduce it further? I'm done. 2 and 3 have no common factors, so I'm done at Mg3P2. All right, that's magnesium phosphide. All right, now we got to throw in one of these polyatomic ions here, magnesium phosphate, PO4 with the -3 charge. And again, it's all about the charges. I'm going to write my Mg, PO4. I'm going to bring this number down here, so Mg3. And now that I have 2 phosphates, what am I going to have to do? Put it in parentheses, absolutely. Boom. In parentheses, I got 2 of them. Okay? Now, again, this PO4 is a package deal. You are not going to look at that 4 and try to reduce it. It's always going to be PO4 in your formula for every phosphate. Okay? So when I'm doing that last step of making sure that everything's reduced, the only thing I'm paying attention to are those 2 subscripts that I just brought down. All right? To be clear, I'm not comparing this 2 and this 4 and pulling out some common factor. The PO4 is a package deal. It's always PO4. All right? So that last reducing step would be only looking at this 2 and this 3. And again, we established that they don't have any common factors. So this would be my formula for magnesium phosphate. Get rid of some of the colors here, but yes, Mg3 and then in parentheses PO4 2. Okay, all right, so then let's go back to the periodic table. Now let's practice going the other way. All right, so what do I mean by that? I mean now I'm going to give you a formula. So for example, NAF and you have to give me the name. Oops, that didn't work. All right, so again, we're going to do the same process, but in reverse. We're going to draw our 2 ion formulas. Sodium, let's find that on our periodic table. Fluoride, oh, I kind of gave it away. F, let's find that on our periodic table. Okay, so we're going to write these ions with their charges. Right? And remember, when we're doing our name, all we're going to do is throw the name of these 2 ions together. So what's the name of the Na plus ion? That's the sodium ion. So this would be sodium. And what's the name of the F minus ion? So not just fluorine, but remember, this is where we have to stick that IDE ending on. So sodium fluoride. All right. Now, this gets a little bit more tricky if we were to throw one of our transition metals in there, one of these type 2 ions in there. So for example, if we did FeCl2, if we find Fe on the periodic table, right here, because of where iron lives on the periodic table, what am I going to have to include in my name? Those Roman numerals. And what do the Roman numerals correspond to? The charge. So now I got a little bit of a puzzle on my hand because I have to work backwards to figure out what the charge of this iron ion is in this formula. That's the only way that I can get my name correct, is to put in that charge. All right? What you always know is your anions charge. Transition metals, I don't know what that iron is, but what I do know is what the other thing is. I do know what my chlorine is. Furthermore, I know that those charges have to cancel out, right? So we're going to work backwards here. What we're going to do is say, all right, I have 2 chloride ions. Each one brings to the table a charge of -1. So what's the total amount of negative charge that we have in this compound? -2. And if it's neutral, what is the total amount of positive charge that I have in this compound? +2. So then what's the charge on that one iron ion? It's got to be +2, right? So now we got to do a little bit of work to figure out what our ion name is. Specifically, we have to figure out what the charge is. We can't just figure it out from the table. And so I got to do, getting my ion with its charge is a little bit more work, but we can figure it out. So this would be iron 2 chloride. Children. All right, now, a lot of people are like, okay, well, why can't I just do like a reverse swappy swap kind of deal, right? If I were to take this number, bring it here, this number, bring it here, that all works out great. And that will work sometimes, all right? But let's do an example where this is going to fall through, okay? This is kind of the long way that I just showed you here. The long way will always work. All right, let's show you an example where that shortcut would not work. Let's do PbO2. Lead, Pb, lives over here on our periodic table. Type 2, can't figure out its charge just by looking. Okay, again, what I do know is my anion, my oxygen. And each oxygen has a charge of what? -2. So this one, and I got 2 of them, right, based on my formula? So what's the total amount of negative charge in this compound? -4. And so what's the total amount of positive charge that I have to balance it out? +4. So that lead ion has a +4 charge. Okay? And if you notice, if we did this reverse swappy swap, it would not work out. That's because this is an example of a formula that after we did the swappy swap, we had to reduce those numbers, right? Because of that reduction step, the reverse doesn't work. Now, you can always try the reverse method and say, all right, well, oxygen doesn't have a charge of -1. I got to do it the long way, okay? But this long way will always get you to the correct answer here. Total up the amount of negative charge you have. You will always know how much negative charge you have because you can tell the charge by looking at the periodic table, okay? Then you got to work backwards to figure out what the positive charge is. So this would be lead 4 oxide. All right, so remember we have to include those Roman numerals for our transition metals. All right, but we're just going to do the name of the cation, the name of the anion. What's up?
So for the chloride, why did you do -1 then on that oxygen?
Because chlorine lives over here in this column where its charge is -1, but oxygen lives over here in this column, so its charge is -2.
Oh.
So I had to look up based on what those ions are, what to put for that charge column there. Let's just do one more. Okay, and actually, we'll do it on this page here. We're going to make it our worst case scenario problem. All right, now every problem on your exam is not going to be a worst case scenario problem, but of course you can expect 1 or 2 of them. Okay, so what do I mean by worst case scenario? What if I gave you something like Fe Fe, well, let's not do blue. Fe2CO3, 3. Now I have a transition metal and one of those pain in the butt polyatomic ions. All right, the name of the game is still going to be the same, right? But it's way more intimidating looking because now I have one of those polyatomic ions. So take a second and see if you can't figure out, based on what we did previously, what the charge on those iron ions would be so that you can name this compound correctly. I have 3 of these CO3s, and I just have to know that carbonate has a -2 charge. That's just something that we have to know, is the charges of these polyatomic ions. It's never going to be anything up but -2, but I have to have that connection in my brain. Carbonate -2. Okay? So now I have 3 of them according to my formula, right? Because it's in the parentheses with the 3 outside. So if each one has a charge of -2, what's the total amount of negative charge in this compound? Add it all up. So then what's the total amount of positive charge? +6. Okay. Now the only other difference between our previous problem here is that I don't just have one iron ion in this formula. I have 2 of them. Right? And we said we don't know what this is. But what I do know is they both have to sum up to that total positive charge of +6. So if I got 2 of them and they sum up to 6, what is each of them going to be? +3. So this compound right here would be iron 3 carbonate. Okay. Name of my cation, the iron 3. Name of my anion, the carbonate ion. All right, so we saved the easiest for last here. All right. These are now what are called covalent compounds. Whereas an ionic compound consists of a metal and a non-metal, a covalent compound is only nonmetals. All right, so for example, CO2. If we look at our periodic table here, carbon lives on the right-hand side. Oxygen lives on the right-hand side, right? They're both over there on the same side of the periodic table. They're both nonmetals. This would be a covalent compound. All right? Now, CO2, I think everybody might have a sense of what that is just from like pop culture. What is that molecule? What's the name of that molecule right there? Carbon dioxide. And so here's going to be the big difference between our ionic compounds and our covalent compounds. In our covalent compounds, we build into the name how many of those elements there are. It's carbon dioxide because there's 2 oxygens. So we have these prefixes that will denote the number of atoms. 1 would be mono. 2 is di. 3 is tri. 4 is tetra. Then it kind of corresponds to geometry class, penta, hexa. 7's a tricky one for people. It's hepta, H-E-P-T-A. Octa, nona, and deca.
Will we be going all the way up to 10? Or?
There is like so seldom compounds that have 10, but there is like one famous one. Generally speaking, you're pretty restricted to this early region here. So let's just do a few examples here so we can see how this works. We had a compound N2O4. All right, we're going to look. Our first element, and we're going to do this by analogy to the one we know. Always go back to the one that you know in your brain. Carbon dioxide. You got that down, right? You can use that as a template for each of these here. The first element is just that element name straight up off the periodic table. All right? So in this one here, it's going to be just nitrogen, but now I have 2 of them, so I'm going to use the prefix di. So this would be dinitrogen. Okay. Now I'm going to move on to my next compound here. Based on how many I have in my name, I got 4. So according to my table, which prefix am I going to use? Tetra. So dinitrogen tetra. But then, again, go to analogy by our previous example. It's not tetraoxygen. We do the same thing to the second element that we did for our ionic compounds, where we stick that IDE ending on there. So dinitrogen tetraoxide. All right, and then the other one, let's do, and then we'll sort of formalize our rules here. Another one that y'all might know just from, I don't know, maybe biology class or pop culture is C, not CO2, but just CO. This is the one that's terrible for you. Does anybody know what this one is? Carbon monoxide. And notice that I use that mono prefix because there was only 1 oxygen in that formula. All right, so we have these covalent compounds that consist only of nonmetals. When we name these complexes here, we're going to use our prefixes. To indicate the number of each atom in our formula. Okay, our first element in our formula, we are going to use the name exactly as it appears on the periodic table. All right, so first element, name off periodic table. Or we could say copy name off periodic table. Okay. The other thing that's a little weird about the first element, and again, go to the thing you know, that carbon dioxide example, we don't say monocarbon dioxide. We'll drop the mono prefix if there's only 1. All right, so for that first element, we're going to copy the name off the periodic table, no prefix, if there's only one. If there's more than one, like in dinitrogen tetraoxide, then we do have to build it into the name. But only one, we're not going to use the prefix. Okay, and then finally for the second element, you have to use that IDE ending, just like we did for our ionic compounds. All right, the other thing that's true for the second element, as we can see with carbon monoxide, is we always use the prefix. Regardless of how many there is, you're always going to use one of the prefixes from your table. All right, so the second element, we're going to use that IDE ending, and we're going to always use our prefix. All right, so just to finish it off here, SO3. Take a second and name that compound for me. First element, straight up like what it is on the periodic table. Sulfur. Second element, what am I going to have to do? Put that tri prefix and turn it into that IDE ending. Cool. All right, Monday, you're going to come in, we're going to do nothing but review. We're going to try to cram in as many problems into that 50 minutes as we can. Don't come in here at Monday at a 0%. I'm not going to be able to get you to 100 by the end of the day, right? You need to come in here at like an 80, and we can fill in that 20% gap. But make sure you're putting in the work this weekend to learn this material.